the re-recording of class number 4, since the last record in the class cannot be opened on my computer, so it has to be just redo again for me. So the class number 4 from the, well, let's pick up first from the previous class. In class number 3 we developed up to class number 3, okay, we developed the stiffness matrix for elements used in the structural analysis, for example the truss and the frame elements. And we also consider the case where we have the special kind of member like non-prismatic member, so we deal with the issue like that already. Now all the stiffness matrices we came up with before are for the local coordinates only, right? But in reality we expect to use the stiffness matrix from members which are not in the same orientation, because in the real structure that you consider, for example the truss structures, you can imagine there are so many orientations of members in one truss structure. So even for the frame structures, the building frame, the gable frame for the factories, and so on and so forth. So you know that members are not aligned in the same orientation, but the equations and the stiffness matrix, the equation I just mentioned is the equilibrium equation between internal and external force. Alright, so these are formulated, okay, I will write it down too. These are formulated in local coordinates, so the directions of the force are aligned with the local coordinates. So here's what we had so far. We have the F equals to the K, which is the local stiffness matrix, times the lowercase u. Well, for here I use the lowercase letter to denote the local coordinates. Now if we have the system of the structure, so I just give you an example. Just like this. Maybe this is just a truss structure. I don't write a support for now. And we have 3 members. All 3 members, they all have their own local coordinates. Alright. So that depends on how you set up the starting node and the ending node. I call it this way. So well, here we have member number 1, we have member number 2, and member number 3. So if we look here, you have C1, C2, and C3. Okay. You can see that C1, C2, C3 coordinates are pointing towards the different direction, and you know that in order to cast the equilibrium equation you cannot just make a summation of force in a different direction like that, right? So we need the universal system to make the equilibrium equation we cast at the nodal point to talk in the same basis, let's say same language. Then we put something, let's say some system. So we issue the global coordinate system. For planar frame system, we have the x, we have the y, right? So basically, for now, if you have this orientation, let's consider the member number 1. Member 1, let's see the sets of parameters or the unknown and variables that we have in this problem. Okay. For member number 1, okay, you have the node, the first node. Let's call this node number 1, node number 2, and this is the node number 3. This is it depends on your choice of calling. It doesn't really matter. As long as everything is done consistently, we will end up with the right solution. Now, here, along the local coordinates direction at the node number 1, this is the first node. If we call it the first node for element number 1, well, you can see that the local coordinate is pointing towards the right, the upper right side. So the left one is the starting node. We call this one the U1. Well, the displacement, which is associated with member number 1 at the node number 1 along the local coordinate is U1. Also, we will have the force that points towards the axial direction at the node number 1 of element number 1, which is the lowercase f1. Well, this same thing is going to happen at the node number 2. Alright, so you can imagine that, well, the way we set up the equation in local coordinates is going to make these sets of variables in, well, let's say along the C1 axis. Well, now if you look at the member number 2, you have the new sets of forces and displacements. You are going to have U1 and F1, but these two variables are from member number 2, member number 2, and they are aligned with the C2 coordinates. So we have U3 and F3. Right, I would like to put a little subscript so that you know the difference between U1 and F1. So I put the subscript 2. Subscript 2 here denotes the member 2, number 2. So there, I put the subscript 1 that denotes member number 1. Right. At least you know that this is along the C1 coordinate. Here is 2 and 2. And the last one, okay, let me write this down. Alright. We have U2 subscript 3 and F2 subscript 3. So it is here U3 subscript 3 and F3 subscript 3. There you go. We have all displacement, degree of freedom, and the force along the axis of three members. So you can see that at each nodal point, number 1, number 2, number 3, we have many forces. They are not aligned in the same direction. Yeah, for sure you cannot have anything. The equilibrium equation cannot be made, right? So how to cope with this problem? We have the C1, C2, C3. We call them local coordinates. We developed the concept of direct stiffness initially in the local coordinates because it is very easy to cast the stiffness matrix of each type of member without any consideration about the orientation at that moment, right? So we separate the issue. First of all, we get the local coordinate stiffness matrix, and then the second shot, we're gonna make the transformation of the information we had previously in local coordinates into the universal language or universal setup in global coordinates. So the x and y, right? Just get yourself used to the terminology a little bit. So the x and y are global coordinates. There you go. Now, how to make our life easier? How to make the calculation possible? Okay, so let me show you here that if we decide to make the equilibrium, okay, to transform the equilibrium we had in local coordinate into global one, then at each node you are going to have the new sets of forces and displacements as you are going to see over here. So now, okay, you can see here that at the node number 1 you have U1x, U1y. Likewise, you're gonna have F1x and F1y. So still the superscripts here, they denote the nodal point that they are associated with. The subscripts denotes the direction. So we create the new sets of displacement and forces at each node in the very same way. So here and here. Now it is the uppercase U2 subscript y, F2y, U2x, F2x. Okay. Oh, sorry, over there. Yeah, I switched them around. Sorry. And the last one, U3y, F3y, U3X F3X. Okay. So the basic idea is to transform the quantities in blue into the quantities in pink. Alright. So member 1 will be transformed into the pink quantities. Member 2 also, nodal point displacement and nodal point force will be transformed into the pink quantities. So they are coming into the universal language. Alright. But there will be a little strategy. It is not as cool as the strategy. It's not that complicated. But well, you need to know, okay, from one point to the next point, what are you going to do here? So basically, we know that the desired shape of the equations, equilibrium equations, we wish to have this equilibrium equation in local coordinates. We want this to transform into the new equilibrium equation in global coordinates. Equilibrium equation in local coordinates. So this is the equilibrium equation in global coordinates. Alright. That means both force and displacement will be transformed, force to this one here, and the displacement to this one there, right? Okay. The burden about the transformation, well, we will later see that thing which is called the direction cosine. That burden will be absorbed in the global stiffness matrix, right? Thus, first of all, let us consider the coordinate transformation in the truss member. First of all, you got to, we're gonna make this element, oh, sorry, now we have the choice of calling or we can set up the element in a very same member like this. You can make this one as the starting point, or you can make this one as a starting point, right? So if we are in the left case, left hand side, we are going to see the local coordinates orientation that look like this, and another one is going to look like that. So here is your C and another one. Now, the way we calculate the orientation angle of the member will be different, because we set up the starting node differently. There we have the first case, we measure the angle of orientation from the horizontal line or the x-axis, and then we open it up along the counterclockwise direction as shown by the arrow here. Alright, and then this angle, we call this angle alpha. Whereas for the different, for this case, we have exactly the same geometry of the structures of this member, but we set up the starting node on the right hand side, and then it is finishing up at the left side. So we are using exactly the same system to figure out the orientation alpha. So we start with the x-axis, and this angle open up along the counterclockwise direction, and then you'll be ending up with this alpha angle, which is pi plus alpha on the left hand side. So this orientation has to be inconsistent with the way we set up the first and the second node of the member. Okay, so let's go to the next page. So we consider that member again. Now we'll try to see how to change or how to convert the quantities from one system to another system. And we used the pink previously. Okay, so call node, this node number 1 and node number 2. So U1x F1x. Okay, I will just do this quickly. F1y U2x F2x U2y and F2y. Okay, now U F1 F1 U2 F2. The first transformation I'm going to make is the force transformation. So we need to write the relationships between lowercase f and uppercase f. So over here, the uppercase f, you can see that F1 x is equal to F1 at the nodal point 1 times, this is the alpha angle, cosine alpha. Well, this derivation will also work with the case like this, because this is the same system of measuring the angle alpha, right? It's just a matter of fact that you might have the different starting node and the ending node, but the angle alpha is measured from the same direction, from the same reference. That means no matter how orientations of the member is gonna look like, as long as you measure the alpha in the same way, in the consistent way, then all these calculations will be applicable. So you look at this, F1 x, now F1 y is equal to, still it is lowercase f1 times sine alpha. And if you consider this, you have the F2 x equals to F cosine alpha, and F2 y equals to F2 sine alpha. These scattering four equations can be grouped up into one set of system of equations, and this way, the way we group them up is actually benefits the setup of the global system of equation later, when you write out the capital letter F equals to the cap K times the uppercase U. Well, so here I have the F1x, I have the F1y, F2x, F2y. I put all of them in the matrix format. So the first is already here. Okay. And well, you know that, oops, this cap F, the dimension is 4 by 1. That means this matrix has to be 4 by something. Alright, but we want to write the global force in terms of local force. So you know that this has to be F1 and F2, which is the 2 by 1. So here it has to be 4 by 2. Okay. Now we put equation by equation into here. So start with the F1x. It is equal to F1 lowercase times cosine. It has nothing to do with F2. As it has nothing to do with F2, then there you go, we have 0 there, and we have the cosine alpha here. So F1y, you get the sine alpha and 0 there. When you now move down to cap f to x, it has nothing to do with f1, so I put to 0 dash for both f to x and y, and then we get the cosine alpha and the sine alpha. This matrix is a transpose of direction cosine, right? So that is denoted by the cap phi letter, and here, so let me put the terminology there. Direction cosine phi. Okay, well, essentially now this is how it looks like, and if you look back over here, you want to transform from the local to global over here, right? Then as you have the f equals to phi times f, then we can just substitute the f by local coordinate stiffness matrix K times U. So both of them are local. Alright, we successfully have the global value in the left hand side, but now we still have the displacement U left as the local coordinates parameters or variable. Sorry. So our goal now is to write U in terms of something multiplied by the cap U, such that the whole thing here is going to be substituted into the local U, and then finally we're gonna have the relationship between the capital letter F times something times the uppercase U. Okay, so strategy is like this. I'm gonna erase this out first for now. Okay, so to write the displacement, local displacement U in terms of global displacement, we are going to consider this member To do so, we apply the global coordinate displacement so here we apply U1 U1x and U1y. So your member will be deformed like this. Well, just to get yourself used to some terminologies a little bit, the brown line is the undeformed configuration, whereas the green is so-called the deformed config. Okay. Please keep in mind that at this moment we are talking about the small displacement. That means it doesn't really change the orientation of the member significantly. It is negligible, let's say. So the picture you see over here is 1,000 times magnification, right? But we need to have this magnification such that you can see how things work, how the members move and deform. So we apply U1x. Then, as we apply U1x, we'll be able to measure the change of the length of the member, which is actually the lowercase u1. So lowercase u1 is actually aligned with the axis of the member, right? As it aligns with the axis of the member, well, you can see it like this. This is u1 lowercase. How about this one? This one you can also do the same thing. And you can calculate u1 in here. So now let's take a look. The angle we have, the orientation, we have the alpha orientation. Okay, measure like this. If alpha is, if you get the alpha there, then this angle is going to be alpha 2, right? And this is the right angle. Okay, so let's write things down. We want to find u1. u1 is calculated from u1 subscript x times cosine alpha, whereas this u1, which is a result from the displacement u1y, is equals to this relationship. Okay, thus we can sum these effects. If you have both u1x and u1y, you will have the u1x cosine alpha plus u1y sine alpha. There you go, we get this relationship. This is the relationships we have from the first node. So we will look at the second node next. Let me move a little bit. Okay. here we apply displacement again through this and through this direction. So this is called U to Y and U to X. The final configuration of the member will be in the green. So like this, also like this, and we can find out the U2 lowercase. As mentioned, we will convert everything, the uppercase U, into the local coordinates. Okay, so these are what you have in local coordinates. Lowercase u2 and lowercase u2. Okay. From this picture, the angle alpha is here, and this angle is equal to alpha. So we write the relationships between lowercase and uppercase displacement variables. U2 is equal to uppercase U to X. Okay, we take the component in the actual direction, you get the cosine alpha, and for this case U2 equals to U to Y sine alpha, and that makes the U2 equals to U to X cosine alpha add up with U2 Y sine alpha in the case where you have both X and Y displacement. Well, we will take these relationships for U1 and U2 from the previous page, right, and this page, and then we put them together. So we write the U1 and U2 in terms of some sort of matrix, of course, matrix equation. This first one is 2 by 1, and the second one you're gonna have all variables in the global coordinates. That includes U capital letter X, U1Y, U2X, and U2Y. Okay. So 2 by 1 is the 2 by 4 and 4 by 1. Okay, so U1 is equal to cosine alpha U1x sine alpha U1y 0 u2x, 0 u2y, and here cosine alpha and sine alpha. This is the direction cosine. Matrix. Okay. This is the uppercase U and this is the lowercase u. So I write them down in one. Okay. These relationships here will be used along with this one. So let's copy this and make use of it in the next page. So we revisit this equation and we find that the whole thing here is going to plug in there. So that means the phi transpose times the k, well, this is still local. Phi and u. Okay. So this is your uppercase K global stiffness. Look, I should put it this way. Stiffness matrix in global coordinates. Okay, this is just the element okay, this is not yet the system. Well, we will put together the elemental stiffness matrix later into the system of the structure. Okay, so your homework, number 3. I just want you to expand. You have this phi, right, as a function of alpha. It is a trigonometry function of alpha times the lowercase k. That lowercase k is actually the EA over L minus 1. This is for a truss element, right, as you know. This is transpose and then phi. So get the final form of this. That is going to be something like EA over L outside. And then you're going to have the matrix inside there. This matrix is going to be 4 by 4. Am I right? Because that phi is 4 by 2. This one is 2 by 2. And this one is 2 by 4. So you will end up with the 4x4 size. So in there, this is not 0. I just make the circle so you understand that there will be in total 16 entries. In each entry, it could be sine and cosine, okay, sine square, cosine square, or sine times cosine. The sineness of each one you should check very carefully, and then all scaled by EA over L at the outside, okay, to make it easy for you to look at. Okay, this one will be compared with the following derivations of the stiffness matrix in global coordinates, straight, without the use of local stiffness matrix, the lowercase k. Okay. So basically, yes, you can compute the stiffness matrix. Okay, I will copy from here. You can compute the stiffness matrix in global coordinates by doing the same thing as the first class. You don't necessarily have to apply displacement along the axis. You actually can apply the displacement along the global coordinates. So we first do this, and then you have the following deform configuration. This deform configuration here, you will have the internal force. So you have U1x going on here. If you apply displacement U1 subscript x, you will find the internal axial force by computing the change in the length along the axial direction, which is here U1. Let me clean it. Okay. So you compute U1 from U1x by U1 is equal to U1x cosine alpha. This axial deformation will cause the axial force, which is equals to F1, right? So F1 is actually along this axis. F1 is going to be the force resistance of it. You will need to F1 equals to what? Strain first, right? If you want strain, you need the U1x cosine alpha divided by the length L, you get strain. and then to get stress you multiply by E. To get the force you multiply by A. Now you get force F1. Force F1 has to be it is along the axis of the member. So we need to apply the capital letter uppercase F1x like this in order to make the node displace in this way, okay, along the U1 without turning on the U1y. So the F1x will be computed. F1x is equal to F1 multiplied by what? The angle is still this alpha cosine alpha, which is equal to EA over L multiplied by cosine alpha square times U1x. Now we can get F1x. You need to compute F1y later. F1y, we still need the vertical force. Let me find a place to write it down. We still need this vertical force to make sure that the node will not go down, right? If you displace it to the right without the force pushing upward, this node might drop down, and that is not the concept of getting the stiffness matrix. We will turn on one displacement at a time. So we have the F1y applied like that. That is F1 times sine alpha, and then you will end up with the EA over L cosine alpha times the sine alpha U1x. In the meantime, you need something to counterbalance so there are F2x and F2y. I put the absolute sign there because it is just the magnitude, but later on when we talk about this F2x, F2y, we will put the sign so we can understand how, or the directions of the point force, F2. So we have the F1, the magnitude will be the same, it's just the difference is the sign minus EA over L cosine square alpha U1x, and F2y is equal to minus F1 times sine alpha equals to minus EA over L cosine alpha times sine alpha U1x. You get all of this, right? The next step is to conduct the same thing. You just need to change from the apply U1x to the U1y. You're gonna get this deform configuration. Okay. and the u1y will cause the change of the length along the axis of the member, that is u1. Okay. The angle here that we have is equal to alpha. So first of all, we need to write down the relationship between u1 to u uppercase u1y, like so. Now we know the axial deformation caused by uppercase u1y. We can calculate strain. The strain is equals to u1y sine alpha divided by L. And then your strain will lead you to stress by multiplying by E. And from stress, that makes the axial force. Okay, that axial force will be then computed. Well, we will find the component of that axial force in the x and the y direction. So the component of this axial force will be this is F1y F1x and F1y. So now we calculate F1x is equal to the F multiplied by cosine, right? Alpha. That is going to make EA over L. We have sine there, okay? So we have sine alpha times cosine alpha u1y. F1y is equal to sine alpha, alright? EA over L sine square alpha u1y. And then you can find the corresponding forces that makes it. Let me move all these things up. F to y, F to x. Okay. So F to x is equal to minus EA over L sine alpha cosine alpha u1y. F to y is equal to minus EA over L sine square alpha u1y. Alright. Let me put the absolute sign there, because here I just point the head of the arrow towards the direction that will be conducive for you. It is understandable that the F2x will be pointing towards the direction opposite to the F1x, right? Likewise for the y direction, so they need to balance for the equilibrium. Okay, but down here the sign does matter. Okay, up there I just put the absolute. Okay, so hope it's not confusing. Okay, so what happened from here to the next page then? Right now you can make this F1x is equal to, first, F1x is equal to EA over L cosine alpha square U1x. So let's pull out the EA over L in the bracket. Okay, we have the cosine square alpha. The next one is the cosine alpha times the sine alpha. Alright, and we have not finished the whole thing. And what else? U1x, U1y, you're gonna have U2x and U2y. Move it up a little bit. Okay, so you'll find the remaining two out. Okay, you get the first equation, this. Okay, so the second one will be F1y. F1y equal to EA over L. Sine alpha times cosine alpha, and then sine square alpha, and you're gonna continue by yourself. This is going to multiply by the u. Okay, finally you'll be able to write this relationship again. F equals to K times the times the uppercase U. So this K here must be identical with the phi transpose K phi. Okay, you need to compare these stiffness matrices, which are from two different derivations, the approaches, but you'll be ending up with exactly the same matrix. Okay, so we are going to continue in the next video with the derivations of the stiffness matrix and the transformation of the stiffness matrix for the planar frame member. See you.